Here you can see what the breadboard is going to look like when you arrive for lab today. We have over here on the left two flip-flops, two JK flip-flops. It's actually two chips, each of which contains two JK flip-flops, so we can handle up to 4 JK flip-flops. I have a single AND gate chip here, and I have a single OR gate chip here. Originally I had 2 AND gates and an OR gate, but it turns out that you don't need 2 AND gate chips. So I took out the other one. So we have a JK flip-flop pair, a JK flip-flop pair, an AND gate, an OR gate, 3 LEDs here which are going to display Q sub C, Q sub B, and Q sub A. And then over here we have a reset switch, and then we have the clock circuit, which is generating a clock signal of about a 2-second period. I put together this little template to try to illustrate what each of these chips is doing, because it's going to be important for you to be able to identify how to access each individual element of the flip-flops. Realize that the left half of this flip-flop, of this first flip-flop chip, is going to be Q sub C. If you look at the pinouts, there are the Q's are going to be Q sub C bar, there'll be J sub C, K sub C. Then the right half of that same chip is going to be Q sub B. So it'll be the Q sub B bar, J sub B, and K sub B. Then the left half of this chip is going to be Q sub A. So it'll be Q sub A bar, J sub A, and K sub A. And then the right half of that chip is unused. We're not doing a 4th flip-flop, so you don't need that one. And then over here we have an AND gate. There are actually 4 AND gates built into that one chip, and then 4 OR gates built into this chip. So what you'll need to do is either route signals directly between these two flip-flops, or you'll need to route them over to the AND gate or over to the OR gate to generate the signals that are going back into the J's and the K's. And so when you've wired the device up to be an even-odd counter, this is what it'll look like. You can see that I have a number of connections that are made here. These include, for example, making connections to the clock. I have to make all of the J and K inputs for each of the 3 flip-flops. And then I also have these 3 wires here, which are routing the output signals, the Q sub C, Q sub B, and Q sub A, over here to these LEDs. And you can see that I can push the reset button to put it back to 0, and then it will go to 2, and then it will go to 4, and then it will go to 6, and after 6 it will go back to 1, after 1 it goes to 3, after 3 it goes to 5, 5 goes to 7, and then 7 goes back to 0. So it is in fact correctly doing the even-odd counting through all the even numbers first, then counting through all of the odd numbers next. And it probably involves maybe about 12 to 14 wires that you need to make the connections to. And here you can see what the modulus 5 counter looks like when it's been properly connected. Again, we have the clock signals. The clear bar signals were already connected, and so our main job was to calculate the J sub B, the K sub B, and the J sub A, K sub A, J sub C, and K sub C. I've actually modified the circuit that you're going to see when you arrive so that it will have just one AND gate chip and one OR gate chip. We don't really need a chip here, but you can see that over here I'm displaying Q sub C, Q sub B, and Q sub A on the 3 LEDs. And then this mass of wires here is calculating the J's and the K's. You can see, for example, if I reset, it goes to 0, then it will count to 1, and then it will count to 2, and then it goes on to 3, then on to 4, then on to 5, and if I've done my job correctly, it should go back to 0, 0. And then it's difficult to see that cells or states 6 and 7 will go back to 0 properly, but I think if I sort of boot this one up, it goes into state 7. Oh, there's 6, and back to 0. And then it will continue on with the count. Maybe it'll go into 7 if we're lucky. There's 7, and then back to 0. So we were actually, by lucky chance, we were able to verify that both states 6 and 7 go back into state 0, and then they go back directly into the sequence. We can also see that the reset switch also works properly. So we have a fully functional modulus 5 counter. It's known as self-starting because if it goes into one of those 2 unallowed states, it will automatically go back into state number 0 again.